recorded, please let them know that it is recorded. Recording is live. Yes, thank you. Oh, yeah, it shows up here on my screen as well. And I'm going to share my screen with you. Start the broadcast. So that should be all right now. Can you see the screen? Is that visible? Wonderful. So just a quick check. What's on this? Did I just? Yes, a smiley. Actually, I heard on the radio today they did a sort of game show, and there was a question about the smiley. Do you actually know how much this smiley made the person who invented it? How much did that person get for the smiley who came up with this idea? 1 mil? So apparently the answer is invented in about 1962 or something like that. And it was a design for a small insurance company in the US. And they paid the designer actually $45 US. And now you can see, so quite a few people were fairly close. And you would think something like something iconic that, you know. Yeah, $45 US. It's a good retirement, but don't spend it all in one go. And I know we've got probably, well, yeah, I suppose it was more worth. $45 were probably, I don't know, maybe around £200 in today's money. I don't know, have no idea. Well, I would guess something in that range. So be careful with your ideas, with your inventions. And actually, I will talk about something like that in week 12 when we discuss sort of the past of DNA discovery. And I know that my colleague, Dr. Peter Ellis, has done a little bit on DNA discovery and experiments and things like that. He did, didn't he, in BI 324? Is that right? Yeah, $382. Yeah. Yeah. Did he tell you the story of picture 51? Did Peter Ellis tell you the story of picture 51? No. Ah, brilliant. So he leaves that to me. Wonderful, because this is a story of crime, deception, sexism, miscommunication, which actually changed the world. And it is a total thriller. But before we get to that, what I want to do with you in this session today is sort of a little wash up of the practical that most people did either on Monday or yesterday on Tuesday. And because there is quite a bit that we can learn from it. And obviously, I want to share that with you. I am also aware that there are some people who did not do the practical by design, because some students are doing a remote learning, or some students are on degree programs where they are not required to do the practicals. And of course, we had a few students who were not very well or in self-isolation. And it is absolutely correct. There is no write-up. You don't need to do a write-up. There's only the online quiz. And I still haven't given you a deadline for that. So what I like to suggest to you is do this quiz, because it will be of benefit to you when we then go into other things later on in the term. I need to whether I need to give you a deadline, whether I need to make this mandatory. At the moment, I'm inclined to say at the moment, you've got a lot on your plate with getting organized, sorting out the multiple choice quiz on Friday. Get your head around that. Stop panicking and all these things. As I said, there is no write-up, and just do the quiz because you will benefit from it. Okay, so, and before we get started, please don't forget Moodle and the attendance, and I think that's open at the moment. Right, so what we did in the practical, for everybody who was unable to attend or did not attend for whatever reason, we took the solution of Paranitrophenol, and this was a 0.5% weight per volume solution. And I would be very grateful if people could mute themselves in this case. Because I know that some people are on the watch. And lo and behold, so we have a 0.5% weight per volume solution of that. That was this yellow solution that people used. And in the videos and in the lecture last week, we calculated the molecular concentration of this solution. And if I was correct, we used the calculation 5 divided by 139. This was 5 gram divided by 139 gram per mole. And we got something along the line of 36 millimolar solution that we had our paranitrophenol in it. We also then did a quick, so that was the original solution in this little tube that you received. We did a calculation for the absorbance. Of course, we were unable to measure the absorbance of this solution. We had an extinction coefficient at 405 nanometers for that. And the extinction coefficient, if I remember correctly, was 1.83 times 10 to the power of 4 per molar and per centimeter. And from that, we were able to calculate the absorbance of this solution. And we got something around 660. And that, of course, is an incredibly high concentration. I told you, you can't measure anything much above 1. I know that some people tried, and they got a little bit disappointed that they couldn't measure anything. But I think it was a really good learning experience, because you saw that, it is too concentrated. And I would really appreciate if the person who has their microphone open could actually mute themselves. That would be very much appreciated. Anyway, what we did then with this 36 millimolar solution is we made a 1 in 100 dilution. So 1 in 100. And this was achieved by taking 30 microliters of the stock solution from here and adding it to 2,970 microliter. Okay, I think we are back on track. So that's great. So we added 30 microliter of the stock solution to 2,970 microliter of the sodium hydroxide solution. And we had 30 microliter then in a total volume of 3,000, which of course gives us the same as 1 in 100. Okay, so we are back on track. So this was a 1 in 100 solution. And what we can do now is we can calculate with this dilution factor. All we need to do is for our working solution that we did. So that's our working solution. And all we divide our stock solution, the 36 millimolar, divided by 100, that was the dilution factor, and we get 0.36 millimolar for our working solution. And for the absorbance that we started with 660. Now the 1 in 100 dilution is also 660 divided by 100, so that is 6.6 absorbance. And again, some people tried to measure that, and again, they observed that the spectrophotometer couldn't measure it, and they saw a sort of something saying larger than 3. That indicates that the spec can't deal with it. And the 0.36, that was the 36 millimolar solution that we used. That was our stock solution. That was the yellow solution, which we diluted 1 in 100. So that gives us 0.36 millimolar. We then did another dilution, and this was a 1 in 30 dilution, and you did that in the cuvette. So you took 2,900 microliter of the sodium hydroxide solution and you added 100 microliter of this working solution. So if you blanked the cuvette that had these 2,900 in it. That is what you blanked, and then you added the 100 microliter of the working solution. So we had 100 microliter of the working solution. Working solution in a total of 3,000 microliter. In the total volume, that's the 2,900 plus the 100. And of course, that would give you a 1 in 30 dilution. So when we started with 0.36 millimolar, then that is what we diluted, divided by our dilution factor of 30. That gives us 0.012 millimolar, which is the same as 12 micromolar of our Paranitrophenol solution. And of course, we can do the same thing for the absorbance. So the absorbance, again, we had 6.6 in our working solution. We divide this by the dilution factor, and therefore we would get an absorbance of, well, 0.22-ish, more or less. Did anyone get, say, between 0.2 and 0.25? So did anyone get between 0.20 and 0.25? 0.22 exactly. So I have to say, guys, I'm incredibly pleased that you got close to the theoretical value. And I think that's really great stuff. I'm delighted to see that. Now, for those who didn't get this range when they did it, I would say it's great because you now know that next time you do some pipetting, it probably there are things that you still can learn. I'm fully aware that you are not. I'm fully aware that you are not fully trained technicians or fully trained scientists. So if you don't get into that range here, don't be disappointed. It will come with time. And it's really important that people practice this thing. So this is what you did. And I think Ella makes a very, very important point. She said she repeated it twice. And this is actually something that we are going to discuss in probably tomorrow or on Friday. What we can do in order to improve our accuracy and precision. And these are terms that we will discuss quite extensively then. Some people, when they put the sample into the spectrophotometer, they discovered that the spectrophotometer reading actually moves around. So, for example, it starts at 0.3 and it continuously drops down. Did anyone observe that? So quite a number of people observed that the reading wasn't stable at the beginning. And again, that is something that happens very, very frequently. It can go down or it can go up. Either way, And the reason for that is absolutely right. It's an issue with the mixing. So what happens is that if you haven't mixed properly, then there are what is called inhomogeneities in the cuvette. And there might be a cluster of paranitrophenol molecules in one place when there is nothing in another place. And depending on where the light goes through the cuvette, it can actually detect these clusters or not. So that is when a reading in a spectrophotometer is not stable. So a very important lesson from that is if the reading in the spectrophotometer moves around, this is very often an indication of insufficient mixing. And in future practicals, I will actually show you how you can avoid this problem. So sometimes it's not terribly straightforward to do that. And sometimes actually, and we will do a sort of a practical, although it's probably a virtual practical, we will see that sometimes it is desired that there is a change in the absorbance over a time interval. Okay, so if you observe a reading moving around, is nothing terrible, it's just a mixing issue. Oh, yes, you can mess up a virtual practical. And I will make sure about that. Because if everything goes smoothly, then there is no surprise in it, is there? And if there's no surprise, then our brains are sort of wired for saying, oh, yeah, okay, so what? Yeah. So I design sometimes experiments so that you are surprised. And uh, actually, you then did something. No, it's not devious. It's not me being mean. There is actually really good research about that to indicate that you learn more when things have an unexpected outcome. And I want to make use of that. I'm a strong believer that, things going smoothly is great. Things not going smoothly, it makes people think. Konrad, yes, in a way you are right. I mean, when I did my chemistry degree, um, we had to isolate and identify compounds. And one day, the person who was mixing these compounds together made a mistake. So we carried out a routine procedure to isolate some of the ions. And there was almost an explosion in the lab because the person put the wrong things together. But we will never, ever forget that because we now know that certain compounds cannot and should not be mixed. Yeah, it went absolutely boom, and there was a column of fire from the bench to the ceiling. It was really spectacular. Okay, so one thing that you hopefully were surprised was when I asked you then to add to the cuvette 20 microliter of an HCl solution. Remember that? So what happened in this case? Did you observe something happening when you added the HCl solution? Sorry, I just had to let the dog go out of the room. What happened? It went down to almost zero. And I asked people, what is going on? Some people also observed that the solution in the cuvette that the color of the solution in the cuvette changed. It was sort of yellowish color, and when you added the HCl, how did the color change? Yeah, it became almost, liquid pale watercolor. So something is going on. So I asked some people what's happening, and some people said there is a neutralization reaction, or the hydrochloric acid reacts with the sodium hydroxide and things like that. Yes, sort of, yes. Shall we have a look at what's happening actually in this case? Yeah. So the best way to start with is to draw the structure of the paranitrophenol. And I don't know if people want to do that. You try it first. See if you can draw the structure of paranitrophenol. So, and obviously it would be very difficult to post that. So we have phenol, and I draw it like that. This is phenol. And just for the sake of clarification, these dashes here are free electron pairs. And the para actually means that the nitro group is exactly opposite the OH group in the phenol. So the para position would be here. And let's draw the nitrogen and the oxygen. And it would look a little bit like this. So here this oxygen is negatively charged. The nitrogen is positively charged. Please, if there is a fire alarm, you need to evacuate. That's absolutely important. But the session, of course, is recorded, so you can watch that again. So we have this nitro group, and obviously the electrons in the nitro group can sort of move around a little bit. So this would be pretty much the same as, and I just draw the nitro group here, NO. Here we've got the minus, here we've got the plus. So basically the electrons can move around a little bit. But that's not really the important part. What actually happens is we used sodium hydroxide solution. So we had lots of hydroxide ions in our solution. And at in this particular environment, our Paranitrophenol actually didn't look exactly like I have drawn it here. The Paranitrophenol actually looked like this one. Here we've got the negative charge, here we got the positive charge, and here we've got a negative charge again. So this is when we are in the presence of sodium hydroxide. The proton is released and basically forms water. So paranitrophenol is actually an acid. It can donate a proton. And we will talk about acid and base pairs in one of the later sessions. So this is the molecule that we actually observe when we are in an NaOH solution. Now, let's have a little bit of a closer look at what this molecule is. Is this molecule actually, is it aromatic? Is it aromatic? People say yes. And they are the lone or free electron pairs around the oxygen. So let's have a look. To be aromatic, there needs to be a few rules. So firstly, it needs to be a ring. Is it a ring? Yes, it is. Is it a heterocycle or a homocycle? Hetero or homo? So in a heterocycle, we would have atoms other than carbon in the ring. So we would have something, for example, like an oxygen in here. That would be the definition of a heterocycle, but obviously we don't have that. So we have a homocyclic system with no other than carbon atoms in the ring. But even if it was a heterocyclic ring, it could be aromatic. Now, let's look at the carbon atoms in all positions. What is the hybridization of these carbon atoms in these 6 positions? What is the hybridization of all the carbons in the ring? People did their homework. Yes, it is an sp2 hybridization. And if you are unsure about it, then watch the video on hybridization, which are up as well. So it's sp2, and therefore the ring is planar. And we need one more critical information. We need what is called the Heckle Rule. That is the amount of electrons in the ring that form this pi system, the pi bond system in the ring. And these are basically these electrons here. Okay? And absolutely right, Edmila, we have the Heckle rule, which is 4n plus 2 electrons in the ring. That's the Heckle rule. So if n is, which is a natural number, if n, for example, is 1, then we would, for n equals 1, we would have to have 6, 4 times 1 plus 2, 6 electrons in the ring. And we have 2, 4, 6 electrons. So this system is aromatic. And there's no doubt about it. Now, let me draw this again. So we have this one here, negative charge. Negative charge, positive charge. So that is what paranitrophenol looks in solution. Now, what we can do is we can move electrons around a little bit. So, for example, here comes the dreaded curly arrows. This arrow, this electron pair, can actually move in that direction. Then we have a lot more movement. And these curly arrows actually indicate which direction the electrons move. So let's draw our movements. O, N, O. So here, the oxygen, the first electron moved there. We have a double bond, and we have 2 lone pairs. In the ring, here, this pair moved to the side. This pair still sits there. This pair moved down here and forms a double bond here. This pair here moved out, and we've got a negative charge here, and nothing much happens with this guy here. They're still negative, and we are still positive with the nitrogen. This is what the paranitrophenol pretty much looks when we have an NaOH or alkaline environment around it. We're just moving around some electrons. Now, the big question is, what happened to our ring? Here we said the ring was aromatic. You told me that. What happens to this ring here? Is it aromatic? I really get mixed messages here. Some people say yes, other people say it's anti-aromatic. Is it flat? Is that dude flat? We can answer this by looking at the hybridization. What is the hybridization of these molecules, of these carbon molecules? Yep, you're right. It is sp2. So all the carbons are sp2 hybridized, which means it is flat. It is indeed flat. We have all the double bonds sort of can communicate with each other, so it is a conjugated system. That's another thing for aromaticity. Absolutely right. Now, what about the Heckle rule, the 4n plus 2? Is the Heckle rule still applicable in this case? It just does not have the rule. Absolutely right. We don't have the Heckle rule. So therefore, the system is no longer aromatic. In fact, as people pointed out, we have the case of 4n. So we have 4n pi electrons in there, 2, 4 pi electrons in there. And 4n is indicative of what people said, a property called anti-aromatic. So this paranitrophenol, when it is in an NaOH environment, is it Heckle or Heckle? It is actually Heckle. Good question. The electrons in the nitrogen are fixed in this position here. They would not move, and therefore they would not contribute to the pi bonds. So now what is special about this guy here, about this resonance structure? This is also called a resonance structure. Resonance structure is that this structure, let me just get rid of that, because here comes the big thing. This resonance structure has an extinction coefficient of 1.83 times 10 to the 4 molar per and centimeter per at 405 nanometer. So this resonance structure that I've drawn here, This actually absorbs the light at 405 nanometers. So 405 nanometers, this structure absorbs. And that is actually what we measure. Now, when we add the hydrochloric acid, what we do is we actually add the proton again to our system. We add this proton, that is from the hydrochloric acid, and we cannot, therefore, form this structure again, this resonance structure. Is not possible because the electron, this electron pair that we have here and that we previously flipped in here, as you see here, this electron pair that we flipped in here is actually fixed in the hydrogen with the proton here. So we can't form this resonance structure. So if we can't form this resonance structure, we don't have anything that will absorb at 405 nanometers. And that is exactly what you observed. You added the hydrochloric acid, you added the proton here, and in a way, you removed this resonance structure, this blue one here. You basically killed it. And therefore, the substance was no longer absorbing at the wavelengths that you used. And therefore, the spectrophotometer showed basically 0. Does that make sense? And it's not non-aromatic, it's anti-aromatic. It's exactly the opposite of aromatic. If it didn't show 0 or exactly 0, this could be that I've designed the experiment that we did not have to add too much hydrochloric acid because then you get other effects. So I was aware that in some cases there might still be a little bit of the resonance structure left, which you then, of course, would see as a slight absorbance. So if it didn't go down exactly to 0, that's not a big problem. What I wanted you to see is that there was a big drop actually in absorbance. Now, for some people, the absorbance went up. And I'm still trying to figure out what might have happened in this case. According to the laws of chemistry and physics, I consider that a true miracle. It should not and it cannot go up. So I would say it would be very interesting to repeat this experiment and see if it still goes up. Because if it does, then it's a little bit like almost, how shall I phrase it? Somebody being able to walk on water. I consider this a miracle. In the presence of enough acid, you have no longer the resonance structure, and it's only the resonance structure that will absorb light at 405 nanometers. In a way, Ella, yes, this is what you can say. So when there is HCl added, we still have a lot of movement of electrons in here and in here, down here, here and here, but we do not form the anti-aromatic resonance structure, and it is this resonance structure that actually absorbs the light. So if we don't have the resonance structure, we cannot absorb anything. We cannot absorb light at 405 nanometers. And therefore, there is no absorbance reading. You probably can still measure Paranitrophenol, and I would assume that it probably absorbs in the range of 230, 240 nanometers. I guess this is where absorbance happens, but it's not happening at 405 nanometer because there is no resonance structure. We have killed the resonance structure by adding the acid. Uh, well, in a way, we have fixed the delocalized electrons in the resonance structure. So in this structure, the electrons actually in the resonance structure, let me highlight this again, in the resonance structure here, the electrons can still be excited. We need to have the right wavelength at 405 nanometer. So that's the right wavelength to excite the electrons. And the electrons are still, to a certain extent, delocalized, especially here in the nitro group. But they are not as moving around as we, for example, see in the non-resonance structure. Do they add only if you are very, very brutal and have very high proton concentrations, then you probably see addition of protons here to the oxygens. But that would mean you have to add a lot of hydrochloric acid, which I try to avoid because then you see other effects. So I think we've done a lot of chemistry today. Hopefully, you learned that doing these experiments can lead to some really interesting observation, and there is a lot to learn from it. So one thing that I will pick up in the future is how can we improve our accuracy when we measure something. So that will be something that we are dealing with at least on Friday, maybe tomorrow even. So we will learn about accuracy and precision. And we will also need to look at how can we actually avoid that we have these sort of fluctuations, these pH fluctuations. Because you probably noticed we added just a little bit of hydrochloric acid and we had this dramatic effect. So how can we actually avoid such a dramatic effect in future? And that is when we talk about acids, bases, and the dreaded word buffers. So I hope this makes sense. I hope you enjoyed this session, and thank you very much for watching. Get prepared for your BI 300 multiple choice quiz part, and also prepare for the other modules, because on Friday, I think Friday before lunch, you have this program level multiple choice question, to which I wish you already good luck, but I will see you tomorrow in another session for BI 308 and BI 300. Thank you very much. See you soon.